Welcome friends to this session of our discussion. In the previous class we are discussing about the performance index. So, we have discussed about the optimal control problem formulation we are discussing, in which the first we have seen the mathematical description of a model. In the for a linear time varying system we have seen how we can represent a model. General model we will discuss little bit later on, and then we are discussing about the what is the specification of the performance index, and we have seen that the performance index we can take it as the minimization of the integral of the square error, let us say minimization of my control efforts, minimization of the terminal cost, and the overall minimization of the terminal cost plus integral square error plus my control effort. I can represent my performance index as given as j equal to x prime f x plus integral of 0 to t f x prime q x plus u prime r u. We are first term representing the terminal cost. When t equal to t f, I am trying to minimize my error. So, this is giving me the terminal cost, and in an interval from t0 to tf, I am trying to minimize the integral of the square error, as well as I want to minimize the control efforts. So, this is when I am representing my system in linear form. In general, we represent our system, if I will take x dot t as f of x t u t t. So, this is my, and y t may be g of x t u t t, where x is my n cross 1, p cross 1, and u is m cross 1. So, this is the general representation of my system, where my this system may be linear or non-linear. The linear case representation we have seen in the previous class, that is x dot t equal to a t x t plus b t u t, and y equal to c x t plus d u t. So, this is my general representation. So, this means this is n number of the first order differential equation. If we are representing, then that will be my general representation. In such a case, we can have the general representation of my performance index as given as s of x of tf, which representing my terminal cost at t equal to tf point, and integral t0 to tf v x u t, this is defining my integral cost. So, in linear case the same I can represent by this. In this case R will be a positive definite matrix, as we have discussed. Q and F. What is the Q? Q is giving the weight to my error, and in case of this I can give a 0 weight to sum of the error, but I cannot give the negative weights. So, my Q may be a positive semi definite matrix. Similarly, the same logic we can apply to the F. So, Q and F will be my positive semi definite matrix, and Q and R are my time varying, because as a general system I am considering a time varying system. It may be linear, it may be non-linear. When it is a time invariant system, then my A, B, C, D matrix will be the constant matrix, Q, R and F. These matrices will also be the constant matrix, otherwise they will be the function of time in case of the time varying. So, in this way we are representing our performance index for a general system and for a linear time varying system. Sometimes some other form of the performance index we can have depending upon the nature of the problem, like we take the time optimal control system, in which our objective is to transfer the state of the system from its initial value to final value in minimum time. There we are not concentrating on the error or control efforts or some other parameter. Here our objective is to minimize the time to transfer a state from its initial value to final value. Such a system we call the time optimal control system, and the performance index can simply be defined as T0 to T dt, because our objective is to minimize the time. We can also have the fuel optimal control system, where total expenditure of the fuel we are taking as a sum of ut, which is my input. So, we are trying to minimize this, which is multiplied with some weight matrix. So, my performance index will be J equal to mod of ut dt for a single, and if I will have the several pi, then this is nothing but the summation of Ri mod of uit. So, depending upon the nature of the problem, basically we have to select what actually will be our performance index. In this particular course, in our most of the discussion, we will consider a performance index given as J equal to S x of t f t f plus T0 to T f v x of t ut d t dt. This performance index. Once we are discussing the problem in general, and once we are discussing the linear systems, then we will consider the performance index given as J equal to x prime f x plus integral T0 to Tf x prime q x plus u prime r u. Time interval again depend upon the what type of the problem we are considering. If my problem goes to the infinite horizon, then my Tf can also approach to the infinity. So, in this way we can define our system as a linear system or by the general representation of the system. We can select the performance index, and next there may appear the constraints on my input and the states. Normally these constraints we represent as ut in between u minus and u plus, where u minus is the minimum value of the u and u plus is the maximum value of the u. Similarly, for the states can exist, they cannot go below a certain level and they cannot go above a certain limit. So, my u and x may be constrained. So, in this particular case we are discussing the problem initially which are the unconstrained problem. In unconstrained problem we can say my limits for the u minus and the u plus goes to infinity, means you can take any value in this, but most of the case later part of the course we will consider that the my u are also constrained. So, if you will place the constraint, then the nature of the problem change. So, in general we can formulate a optimal control problem in the following manner. Say for a given plant, I am taking the general nature of the plant x t equal to f of x t u t t determine optimal u which minimizes the performance index J as x of tf plus integral t0 to tf v xt ut t dt. So, for a given plant, my objective is to find out the optimal value of the ut, which is minimizing my given performance criteria, and further we can also extend ut and xt are constrained as mod ut is less than equal to u and mod xt is less than equal to x. So, this is the complete statement of a optimal control problem. This is my plant, objective is to find out the ut, which is minimizing the j, u and x are constrained. So, we will start our discussion simply by taking how we can get the minimization of j, and as a optimization problem, if I will take, my objective is to minimize this j which is subjected to the constraint. So, this I can treat as my equality constraint, and this is my inequality constraint. So, this is the formulation of my control problem. So, this is the formulation of our optimal control problem. Next we will see how to solve this problem. So, in this course we will use the three approaches to solve this problem. The first one is the calculus of variation, which we will start discussing next to this. Another approach is the dynamic programming approach. We will discuss about the dynamic programming after the calculus of variation, and in these two normally we do not consider the constraint on the controller state. Then third approach is the Pontryagin minimum principle, in which we will consider the constraints and solve the problem using the Pontryagin minimum principle, how it can be utilized to develop the time optimal control problem. So, we start our discussion by considering the solution of the optimal control problem utilizing calculus of variations. What is calculus of variations? So, calculus of variation or the variational calculus deal with finding the optimum value of a functional. What is functional, that we will discuss. It is a very old technique, originated around 1696. Then L. Euler was the founder of this calculus of variation, and till today we are using the Euler equation to solve the variational problem. So, first we will discuss the few basic concept and the definition of the calculus of variation before coming to the minimization problem. Our first definition comes, which is called the function. What is a function? A variable x is a function of the variable quantity t if to every value of the t over a certain range of t there corresponds a value x. This means if we define, let xt to be the function of time t, this means for each value of the t there corresponds a value x. So if I will take a point which is giving me the value of the t, say t1, and this will have the value of the x which we write as x of t1. So if I will treat this, so xt will be nothing but a function for each value of the t there exists a value of the x. So I can say this x is a function of t. For example, we can write this like say t cube plus t square plus t plus 1. So if xt equal to this, so this is nothing but my ft is t cube plus t square plus t plus 1. So for each value of the t, I know there will be a value of the x which I can make a plot here, and that whole is represented as a function of x. This normally we already have studied at our, in many subjects we use the function as a x. Our next definition is comes out to be the functional. A variable quantity j is a functional dependent on the function x. Like in this case, my x will depend upon t. Similarly, I can have a function which will be the function of the different functions. So I say j xt, if I will write, is a function of xtt. So what I am saying, my j is a function of x. So functional will also called the function of a function. This is also called the function of functions. So j may be the function of a single function x, or it may be the function of the several other functions, like say the x1, x2, x3, or even sometimes we say j is a function of x, x dot, x double dot. So if for t there exists a value of the x, then for each x there exists a value of j. So a variable quantity j is a functional dependent on the function fx. It is written as j equal to j of fx if to each function fx there corresponds a value j. So and functional depends on several function. It may be the function of single function, or it may be the function of different functional. Then we define the increment. There may be the increment in a function and increment in a functional. By definition, increment of a function denoted as the delta f, and delta f is simply defined as ft plus delta t minus ft. So what is the meaning of the increment? If t if we change the value of t by a small amount, say delta t, then increment of a function is simply defined as value of the f at t plus delta t times minus value of the f at t point. So, this is called the increment of a function. Similarly, we can define the increment of a functional. So, the increment of a functional j denoted by delta j is defined as j x t plus delta x t minus j x t. So, the increment of a functional we simply defined if x, let us say t will change as x t plus delta x t. What we said, x is a function of time. So, this means if let this is my x t. So, what is the variation in x t? So, if the whole and this is say my x t plus delta x t. So, if my x will change by any small amount, then x plus delta x at each instant of the time there is a change in this. This means at each t1 there will be a change in the value of the x by a small amount. So, I can say this is at this is x t1, this is same as the x t1 plus delta x of t1. So, this means the delta x t is also changing with respect to time. So, this is if x will change by an amount x plus delta x, then increment in functional j is simply defined as the value of the j at x t plus delta x t point minus j x of t, that we are defining here the value of the j at x plus delta x point minus j of x t. So, this is the increment of a functional, and here this delta x t is called the variation of the function. This means we are saying the function x will have the variation delta x at each instant of the time, and we are representing the whole as a x plus delta x. Then we define the differential of a function. So, first we define the increment. So, let us consider a point t equal to t star. Then t will change from t star plus delta t. Then we can define the increment in function f t as delta f as the f t star plus delta t minus f of t star. So, if I will expand this, with Taylor series, then I have delta f to be f defined as the t star point plus del f by del t delta t plus 1 upon factorial 2 del 2f t star by del t square plus some higher order term minus f t star. So, I can cancel out this. So, this is basically the expansion of f t plus delta t using the Taylor series. So, if I will approximate to the first order term, if delta t considered to be very small, as delta t approaches to 0, so I can say delta f by delta t, say I can put the limit t tends to 0. So, I can define this as my df by dt, which is called the differentiation, or delta f can be defined as del f by df by dt into delta t. If I will neglect second and higher order term, so in this case my delta f can simply be written as df by dt delta t, which is nothing but my f dot of t, which is at the t star point delta t, and this I can approximate as my df, which is nothing but the first order approximation of the increment. So, if I will get the first order approximation of my increment, which is in this way, say if we have taken the partial derivative, if t is constant, I can also replace it by my exact derivative d by dt. So, we call df to be the differential of f at point t star. F dot t star is nothing but called the derivative or the slope at t star point, and the differential df is nothing but the first order approximation of the increment delta t. Similarly, we can also define the variation of a functional. So, variation of a functional is nothing but the first we define the increment of a functional. As we have seen before, how we define the increment? the value of the j at xt plus delta xt point minus j of xt. What we are doing? We are expanding j xt plus delta xt using Taylor series. So, what this will be? So, we are expanding j xt plus delta xt. So, my first term will be j of xt, second term will be del j by del x delta x, next term is 1 upon factorial 2 del 2 j by del x square delta xt square, then we have the higher order term minus j of xt. This j of xt will be cancelled out. We are left with del j by del x delta xt plus 1 by factorial 2 del 2 j by del x square delta xt square plus higher order terms. So, if delta x is considered to be very small, then the first term, if you will see, this is nothing but the first order term del j by del x. If you will see the second term, this is a second order term which is del xt of square. This means if xt is small, my all these term keep on reducing. Next term will be del xt cube, which will be smaller than of the delta x term. So, normally in our optimal control, our first two term is of our interest, where the first term we will define as delta j, which is called the first variation, and the second term we define as del square j, which is nothing but my called the second variation. So, the increment of a functional, if we will see, the increment of a functional is nothing but the summation of my first variation plus second variation plus third variation and so on. So, in the increment of the j, if I will see what actually will be the sign of my delta j, if my first variation is not 0, then its sign will be governed by the what is the sign of my first variation. Suppose we say my first variation is 0, then sign of the delta j is governed by my second variation. Say to find out the optimal value of a function, like I will see x t is equal to t square plus 1. Optimum of a function. So, I know how to get the optimal value of this. So, this I will take dxt by dt, which is nothing but 2t, and I normally equate it to 0. So, in this case, my optimal point is when t equal to 0, and then I take d2xt by dt square, which is nothing but my 2, and from my previous knowledge I know this is the optimal value is t equal to 0, and this is d2x by dt square is positive. So, this value will be my minimum value. Similarly, in case of the functional, the first variation and the second variations are used to determine the optimal values and the point of extrema, means whether this is maxima or minima by using the first variation and the second variation. So, this we will discuss in the later part of our course. So, the first variation and the second variations are the important parameter which we will utilize in the later part of our course. On the basis of the first variation and the second variation, we define the optimum of a function, optimum of a functional, and before discussing the optimum of a functional, we will discuss the optimum of a function. Like we have seen in this example, how we can get these values, that we will discuss in optimum of a function. and then we will start our discussion on the optimum of a functional. So, I stop this class here, and in the next class we will continue our discussion on optimum values, how to find it. Thank you very much.